Oh, okay, let's get started then. So today we are going to talk about Feast, which is actually a feature store, and let me let's touch like start with what a feature store is. Or before that, I think we should start with what is feature engineering as a concept. So we can start with feature engineering. So this is our objective today, and we are going to talk about the traditional approach which we have in feature engineering and how all the feature engineering is being done. And we are going to talk about what is the new normal, like what is the most used term in the recent times, as you all know. So what is happening in terms of future engineering in the near past the last 1 or 2 years. So that's what we're going to talk in the new normal, and then we'll go to feature store, which is our main topic, and what is Feast, which is actually a feature store, and how it is different from other feature stores available, and what are the things which can do with Feast. And that comes to the next objective, which is sort of the problems which actually Feast can solve, and what are the concepts and what are the types, and we also have to discuss about what are the things which Feast does not actually solve, the things which we are actually currently working on the Feast team. So, and we also have a demo at the end of the session which can help you get a clear idea about how to use Feast and how to integrate Feast in your existing ML environment, so that you can make use of this new concept which has come out only a few years ago, like not more than 1 or 2 years. So yeah, so let's get started with that. And okay, so the traditional approach, so what is feature engineering? So feature engineering is basically, if you have to put it in a very simpler terms, feature engineering is something where we have to the process of creating a feature is basically called as feature engineering. It's as simple as that. And but feature, what do you mean by feature? So when we have a machine learning model, so we have to have some kind of an input to the model, which will help us, to train the model and to serve the model in a production environment. So for that, we have a original raw data, and to this raw data cannot be directly embedded into any ML model or any sort of algorithm. So for that, we need to have few characteristics or few statistical computation being done on top of the raw data to understand what it actually is trying to say. The data is basically, it will be very raw, as you say. So it will be like in terms of years, it will be having each and every row will be it can be unique or it cannot be unique. It will have a combination. We have multiple tables. So there are a lot of things which actually will not make any sense if you see it as a whole. So we need to do some kind of computation on top of it to make it understandable and meaningful data. So for an example can be, if you look into a sales data, you can always calculate the average sales in a year, or you can calculate year over year growth in data, or year like growth in sales in a particular year. So all those things you can calculate. So all this additional computation which you are doing on any particular data set, each and every column which you add to it, which is basically makes some data set more meaningful. So each and every column is a feature. So that is what, and the process of getting this feature is actually called as feature engineering. So, and that is actually the problem in hand. What we do in when we develop a machine learning model is we have a data set and we get features out of it and we embed that into the model. So in that part, the thing is it is very tightly coupled, like the data and the model are very tightly coupled. So the process of the code which actually we run to create a feature and add it to the data set, that code is actually very tightly coupled to the whole model itself. So for every new model we have to create a new set of code, have to do a new set of processing which can actually embed the data or process the data beforehand, so that it can be understood by a model or an algorithm. So that is the problem we are having. So as you can see from this slide, that the code for manual feature engineering is problem dependent and must be rewritten for each and every new data set. So that is the biggest problem the current data scientists have been facing. And the process of, to create a feature, it needs a lot of time to build, and it also needs the domain knowledge on which particular domain we are working on. So it needs a lot of domain knowledge as well, and it is actually, this is very time consuming, it's very error prone as well. So these are the drawbacks of the current feature engineering or the traditional approach of feature engineering. So what is the new normal? So the new normal is basically, is like we are going to centralize the storage of features. So Yeah, I think that is pretty much it. We are going to centralize it. The data we have, the content, the features which we generate or we compute based on the raw data, instead of putting it in the same data set and having it coupled with the core or the model, we are going to put it separately. It can be in the different tables or it can be in the same table, but it has to be put in a centralized store or a repository where it will be marked under a particular project or a particular team, or any kind of namespace basically. So we have a namespace, we have a project candidate, and we are going to put the clear features which we created for a particular data set or a particular domain, and we're going to publish it or ingest that particular features into a centralized location. So that is what is centralization, and that is what is the new normal for feature engineering. Because as you can see from the slide, the feature store concept itself was introduced by Uber in just 2017, which is like only 2 or 3 years before. And this concept has been like play a vital role in a lot of ML operations, and people have been following like started building their own feature stores in order to to make use of this concept. And it is actually helping a lot of big companies in the current times. And as per a survey in Forbes, the most 80% of the time of a data scientist is being used for this data preparation and how to do a proper feature selection. So as you can see that how important is feature engineering, based on the statistics which I just gave you. So Uber as a company, they started this concept of feature store. And this is the second point here is actually from Uber's own blog, which says that they have added a new layer of data management, which is a feature store, which is used to share, discover, and use a highly curated set of features for their machine learning problems. So that is what they are doing. So having a centralized store, they have put all the features there, so all the teams across the company can make use of those features. Because if you see that Uber's data will be limited to a particular domain, so they will have details about the drivers, about the cars, about their transactions, and they are limited to a particular domain. So the data sets of features which are being computed, like the daily trips, average daily trips a driver is taking, so what are the kind of feedback they are getting. So these kind of details, these kind of features can be reused across the organization. So that's why they came up with this concept. And it is not only helping in their domain, but it is helping in almost all the domains wherever we are applying any kind of machine learning. We are able to use this feature store. And it is being used by the top companies as we are talking today. So yeah, it's a game changing thing in feature engineering, and as well as machine learning model development and serving. So if you go to the next, so basically now we have an idea what is feature engineering. Now we know what is a feature, we know what is feature store. So basically this is what feature store does. Like, we have a raw data, we add some features, put it into a feature store, and that feature store serves the models. So so this is what a feature store is. As you can see from one of the points, a system that computes, stores, manages, and serves the features in a feature is a feature store. Yeah. So, and the feature store can be a single table, or it can be multiple tables which will have a connection using the primary key, which can be joined using the primary key later on whenever we want. And the each and every table which we create is actually called as a feature matrix. And I think, yeah, so that is feature store for you. And okay, now let's get into what we are going to see today. So now we have a background of what is feature engineering, feature store, feature, and how does the feature store concept works. So what is feast? Feast is actually, like, they have taken FEA from feature and ST from store, and they have named it as feast. It's basically another it's a feature store which has been developed by a company named Gojek in with association with the Google Cloud. So they worked for some time, and they have been continuously developing it. And so this is the architecture which Feast is currently working on. So we have two different type of stores here. We have an offline store, we have an online store. Okay, let me get back to the architecture a little bit later. So let's see what Feast actually does. So what are the problems which actually Feast solves? So that is something we need to understand before we go into detailed architecture. So what are these are the four main problems which Feast actually they try to solve. And The first one will be the models needs to be consistent, and models needs consistent data access with, yeah, consistent access to the data. So what it means is actually, the main important problem we had during the ML, the generating or developing any kind of model is the tightly coupling of the data with the models. So we are have go with the introduction of the concept of feature store, which actually means the decoupling of the features or the data from the model itself. So in that way, because we are decoupling it, the access to the data has to be consistent, and the data needs to be, the data for training as well as the data for serving, both has to be synced perfectly, so that we won't see any skewing in the training serving too, or and there also should not be any kind of the scores which we get out of a model, once we have deployed it in a production, the scores using the same data should not vary. We should be able to get the same score so that we can validate our model, how good is it. So for that purposes, so the data has to be consistent across different layers of a machine learning model development. So that is what they're trying to say in the first point. And deploying, so these 4 points are taken from their own documentation, which actually, which the VC has mentioned in their own documentation, saying that these are the problems they're trying to solve and how are they doing it. So these are the problems in the traditional approach which VC is solving. So, and the next one is very understood by itself, like the deploying new features into production is difficult. So when what we do is basically there's a data engineering team and a data scientist team which is working together to engineer the features and to develop a model. So whenever the modeling or the data preparation team, they create a new data, or they have a new set of statistics added to, a new set of features added to the data, they want those data to be seen in the model immediately. That means they have to productionize it immediately. But the data engineering team or the architects team, they will not be able to, they will not allow it immediately, because they have to do regression testing, and they have to see if the model is stable yet, and that the new data is not spoiling any of the current architecture. So it might take some time. So that is what is being done in the traditional approach. But now we have two different layers, which is like, whenever a data science team or the data preparation team, they are making any changes to the data and uploading it to the feature store, which is automatically being linked to the online store, which is directly directly serving the data in production, side accessing the model in the production. So it is kind of a new layer in between, so which is actually making the deployment of new features into the production very easy. So, and models need point in time correct data. So that is another thing which basically solved, because there is a lot of places where there's chances for data leakage, which will, because there are multiple layers and there are multiple teams and multiple people in a data science, as a data scientist working on a particular model. So there are a lot of possibilities that they might lose the data in between, or there might then there's a new versions of data coming in. So there's a problem, there's a possibility that there can be inconsistencies in the data. So that has to be, and any kind of new feature, any new data is added, the existing features has to be recalculated and made to be need to be up to date as per the data. So that those things are being solved by Feast as a like as a out of the box service, out of the box product itself. So, and the main thing which we already know, like features aren't used across projects, is, yeah, the main idea is to centralize it so that each and every team can make use of that centralized store and go and fetch the features from there if they already have it, instead of spending a lot of time and doing putting a lot of manual efforts to recreate them. So you can directly fetch it from a different namespace or from a different project of a different team. We can just fetch the features from that, and we can make use of it. So that are those are the things, the main major things which we solve. And these are something these are these things are very conceptual wise. These are very much useful for any data scientist to reduce 80% of the time and focus more on their algorithm and not more on the data. So that is these four things cover most of it. So these are the concepts of Feast API. So Feast has, as I told you, projects, which is basically the namespace under which everything comes. So we have projects and then we have entities. So we can see an example, which is this example is similar to the Uber or Ola example, where they have drivers, they have trips, and they have statistics. And the driver trips and driver statistics will have features which are like trips today, and we have acceptance rate, we have conversion rate. So basically we have this based on this data, you can see that we have a namespace and we have entities, which is basically about whom we are talking about. So about which, what kind of data it is. So it's a data of a driver, that's an entity. And then we have feature tables. We have, so here in this example we are not maintaining everything in a single table, we are having in different tables. So we have a driver trips as a separate table, and we have driver statistics as a separate table. And in that we have and these tables will be linked to the entities table using a primary key, so which will be referring when we are used to, when we are going to join it in future. And yeah, so these are the basic API, basic concepts of Feast API. Any doubts as of now, or can I proceed, or do you have any kind of doubts, or do you need more clarification on anything? I'll pause for a few seconds here. No, okay, fine. So I'll take it as there are no doubts as of now, so I'll proceed. um, Oh, okay. So this are the concepts, and we can go to our. I'm actually jumping a few things here, because we can get a very clear idea in the demo rather than the slides. And so I'm just going to show you the demo and how the things actually work, instead of going through a lot of slides. So I'll just highlight the few major things which we have, and then we can actually go for the demo. I think that will be easy to understand. So okay, so the type of stores, so this is the type of stores which Feast actually offers. So the type of stores here are there's an offline store or a historical store, and there's an online store, simple as that. And the offline store is basically to maintain the historical copy. So whenever it is basically like versioning in S3. So we can have different versions of the same data. So whatever, whenever we are updating the data or putting new data into the feature store, then the existing data or the previous calculated features will still be available in the historical store. And the online store is basically it is the latest version or the latest copy of the offline store, which is synced with online store, and that is the store which will be serving directly to the model which is in the production. So in case you want to validate the model, so for that, and even if you want to even if you want to like utilize that data in the production as well, you can do that. So that is online store, which is directly into, it has a very high throughput and very low latency in terms of like, you know, if you compare it with other feature stores. So the response is, the response time is really impressive in Feast. And that is the two stores which Feast offers. And okay, so these are the things which Feast does not solve it. Okay, so Feast has a lot of benefits, but these are things which it's not like these are the things which a Feast cannot do. These are the things on which Feast is currently working on. So they have even the past few days, I have seen few commits, and they have solved few issues in their in their open source repository. So they have been currently consistently working on bringing in these features. And the one of the things is feature engineering, means like we are having so the computation or you know the computation of the features is being done outside, and then the final data or the tables is ingested into the feature store. So that's how the things are as of now in Feast. But what they are working on is they can do the computation inside Feast itself. So that is what they are trying to achieve as of now, and which will be a very big achievement if they are able to do it. And then it's a feature discovery. They are also, like for example, we have ML flow and we have cube flow. There are a few other examples where we have a user interface where we can directly go and see what are the data which is present, what are the projects which are there, and what are the features which have been uploaded or ingested, and which is the current version of the data which is currently serving the model. So all those things are can be should be user interactable, and they should be able to get the information rather than going and calling an API and getting the data. You can they're working on a user interface which will be it will be very easy for people to use these and understand how the data is flowing. And also we have a data feature validation thing which is being currently worked on. And our data validation is currently, it is supported, but it is in a very limited state. We have they're working on providing more validations on each and every features and all the statistics which have been generated, if the features are matching the algorithm, or how the feature selection is being done. So there are a lot of validations which needs to be brought in. So the field team is currently working on it, and they are actually they're going in a very fast pace as we speak, because I have seen few very recent commits, like as recent as yesterday I have seen few commits. So they are working. So let's see if see if they can bring all of these in. But as of now, Feast is providing a really good, really impressive results. So these are the references which I have taken from, and I'll share you this deck later on in our after this session maybe. So you guys can take a clear go through all of this content, and you can try to understand a little more deeper into the feast architecture. So now let's go back to the architecture which we skipped. So this is the architecture which we have. So now I think we should be able to see what Feast is doing in between, and what is the offline store and what is an online store. So we have a data processing where we can do a batch processing from any data lake or data warehouse or any kind of online streaming service as well. So we have Kafka, Kinesis in this architecture. We have batch data as BigQuery. We have GCS, S3, and we also have. So these are the different variations or different forms of data which can be embedded into Feast. And the Feast, what Feast does is it takes the data. The data can be injected into the offline store. And that offline store can be synced to the online store, or it can be directly ingested to the online store also. So once that is done, all the data will be intact and will be consistent, and we can train the data using a single API. Instead of having the data in the model itself, in the project itself, we'll be just calling an API. We'll be passing an entity, and what are the features we need. So it will fetch us those data, and we can directly input that into a model, into a training layer of the development. And yeah, so that's what the architecture is. I think now we you guys will be able to get a clear idea about how Feast actually is it's working. So okay, and that is pretty much it in terms of the slide. So do you have any other questions regarding this, or we can go for the demo? Any questions from anybody?
Hi, I have a question.
Yeah, hi.
Yeah, hi. So this feast, whichever you've said, so is this an open source
Yeah,
API which can be used? Okay, and I understand that it should be kind of a data transformation layer, right? It'll have all the transformation calculations and it'll get updated dynamically as and when data gets updated. Am I right?
yeah.
Okay, thank you.
That layer, the dynamic calculation is the part which currently they are kind of working on. But as of now, as you can
Mhm.
see from the architecture, right? So now what they are doing is they are uh, this layer they are trying to include they're trying to extend this phase into the data processing as well. But that is something they're currently working on. As of now, what they do is they just ingest the data into this. So they do the calculation and then they ingest. So that's what they have been doing as of now. So that is what Feast provides, and it's kind of a centralized location so that anybody can access. Or if you provide access, then they'll be able to go and access the features which are already computed and already present in the store.
Okay, okay. So as of now, the features, whatever we have approved and whatever is present in the feature store, it'll be there, and whoever wants to model with that data can access it.
Right.
But it is not like dynamically the features would be added, right?
No, dynamically, it won't be computed. It won't be computed. This is like the current example, the demo even I have is it has the data which we already computed and we are just putting it. It will be added as a new version, and that new version will be synced to the online store as well.
Right.
So yeah, that's how it works as of now.
Okay. Thank you.
Yes, thank you for your question. And anything else? Okay, then let me take you guys through a small demo. It's a very small example, and I took the example from the Uber's concept itself, because I think you guys are already familiar with the terminologies here which we are using. We have project entities, feature tables and features, and we have driver trips, we have driver statistics, and driver trips in the sense how many trips a driver has done in a day, and driver statistics will cover what is the acceptance rate of a driver, what is the conversion rate of a driver, and about how many average trips is taking in a day. So that will be like on a daily basis. And the average driver trips is is kind of a real time data, which whenever a driver is completing a trip, he'll be updating it in the app or something, and that data has to be entered into the data. So that is for that we're using Kafka in a demo. So that can be integrated with any kind of a streaming service, can be Kinesis or anything else. That doesn't matter. But the point is, the real time data can also be embedded directly into the into Feast. So let me take you guys to the demo here. So I have this Jupyter notebook. So I have all the so this is example we're going to see today. It is like minimal ride hailing example. So ride hailing is basically like to share a car, and whenever you need a service, a ride is being provided, and that is basically a ride hailing. So we are just having a small miniature version of the bigger or the idea or concept of ride hailing. So we're just going to start with a small thing. So here we have the processing layer, which is actually Feast. And okay, so let before going getting into I'll explain how we can install it in your systems or in your existing architectures. So there are, if you are using a cloud architecture, Feast is providing a Terraform template, which you can directly set it up in using EKS in AWS, or you can GKS in GCP, or and even in Azure. They have a Terraform template which supports all three cloud platforms, and you can directly just run this Terraform template, and it will be able to set up a few Kubernetes cluster and a few Kubernetes nodes, which will be serving your Feast store. So as of now, I installed it in my local system. So for that, I just used a Docker Compose file, and it already been provided out of the box. So when you pull the code from their open source repository, you'll be getting all of that together. So you just have to run the Docker Compose file, and it will be setting it up for you. So as you can see, this is the Docker images which are currently Docker containers are running in my system. So here you can see we have a Jupyter, we have this online serving, which will be used to serve the model, and we have a job service, which is actually our Spark job service, and then we have a Feast core, which actually does the Feast original core functionalities, and we have a Kafka, we have a Redis, and we have a Zookeeper thing running, and we have a DB as well. So these are the things, these are the different email containers which will be running, which has to be kept running so that our Feast store is up to date, and it's consistent in terms of data. So these are the same things. This is the same Docker file. So these are the same things which can be used in Kubernetes, or even in any kind of a container service, for example, ECS or anything else. So you can use this. They have provided the CloudFormation, not the Terraform template, so you can make use of it, and have your own own architecture for to manage a feature store. So once that is done, you can directly access all these services from your from any of the services or any of your model development platforms. If you're developing in SageMaker, or just actually using a notebook, then even the EMR notebooks you can do it. So it's just a kind of APIs. You have to call it, and it will be able to do the job. So here you can see we have ingestion. We are ingesting data into the Feast using Spark, and we have historical retrieval, and we have on Feast serving. So this is a model serving, this is a model training, and this is the Feast core job which has been running that I just showed you. So as you go through this example, so what are the things we're doing is you are checking what are the environment variables which are being set. When I run the Docker Compose, these are the variables which are already set, because I'm using a local setup, and these are the I'm not using any blob storage S3 or GCS or storage accounts. So this is my local storage which is being used. And if you want to use S3 for this, you can directly, you can just change this values to any S3 path, so it will be able to pick it up. We don't have to do anything extra to make it work on our cloud platform. So that is one. And these are the other things which are environment variables which are being set up. And then we are going to initialize few variables, like we are initializing the client, initializing a feature, entity. I think you guys can understand what is a client now, what is a feature, and what is an entity, as I already, and this is a feature table. And we have a file source. I'll take you through all of that. So we have a client, we're creating a client first of all, which is a feast client. So once we have a client, we are trying to create an entity. So what is an entity now? Based on the slide which we had, we have a driver. So we are talking to, the data is all about a driver. So that is an entity we are going to work with. So in the driver, the primary key will be a driver ID, which will be unique to a driver. So that will be considered as a primary key, and we have a driver ID name, and we have a driver identifier. That's just a description. And what will be the type of data type of a driver ID? It's going to be in 64. So these are the few syntaxes which you need to follow for creating an entity. So we have just created an entity, and then we'll be having, these are the three features which are being computed on this data. So basically we have ACC rate, which means acceptance rate, and then we have a conversion rate, and we have average daily trips. So these are going to be float, and this is going to be in 32, and these are like three features. And these are the features which are updated on a daily basis. Like at the end of a day, based on the data in the whole day, it will get computed, and that data will be put inside under these columns, and that will be on daily basis. So when you see what is the real-time updated features, these are something trips today. So as I explained before, whenever a driver is completing a trip, he is going to mark the trip as completed, and then that data has to be entered into the database. So that is a feature which is going to come in real time from any messaging service, or any, something like data streaming, Kafka, something like that. So this is, once you do this, it creates a, yeah, these are the features we are creating, and this is a feature table. So this is just a structure. I'll show you how to create a table actually. So here we creating a feature table. So feature table, we are, the name of the table is feature statistics. It is dependent on, it is of the type driver ID. So the entity is basically the driver ID which we created before. And what are the features which are going to be in that particular feature table are acceptance rate, conversion rate, and the average daily trips. Same way, we are having a batch source. That means we're going to do a batch ingestion process, and the batch ingestion is going to happen from a file source. And then the file will be having all these all these characteristics, like the event timestamp will be date time, and we have a created timestamp will be the created column on the data, and we have the what kind of format in which we have the file, which is basically a Parquet format. And we have this driver statistics source URI is basically the path of the file, where the path has been located in a local system, or it can be an S3, or it can be any other system as well. So this is where we are getting the driver statistics source UI, which is something, it is basically my user directory, and this is the folder name which I'm going to give. And so it is going to, once the feature table is being configured, so we know we have features, we have an entity, now we have a feature table as well. The same thing we are going to do for another table, which is a driver trips. And for this also, as of now, we are giving file source as a input for batch ingestion. So these are the two tables we have defined. And once we do that, we are going to just, let me just keep running these things parallelly, so that it will be easy at the when you show the output. So I'm just going to import this, and I'm just going to import create a client, and then I'm going to create a entity, and then I'm going to create some features, and then I am going to directly go into setting the environment for my Spark staging location, and then I'm going to create a feature table, another table. And now I'm going to, this is the client which we created, which is the feast client. So this feast client is going to apply the entity. So basically this entity will get created, these two tables will get created. So before we have just mentioned that it is an object, driver trips is a feature table object. Now we're going to apply it in our feast core basically, or the database, whichever feast is referring to. So now if you see that is done, now we are going to get feature table. So that means the features are being ingested into the feature, the structure of features. Basically, it's not the data, is the structure of feature which has been embedded into the feast core. Now we can fetch it back to see if everything is uh, persisted properly. So if you can, if you run it back, so I'm able to see the driver statistics is the name of the feature table, and entity is the driver, and what are the different features we have, and what is the source for it. Now we have the source file URI as well, and the same for the driver trips. So now we are going to populate the table which we have now. So here we are going to do is we are going to generate entities which is random. We're using NumPy to generate random values, and we're going to put it inside for this example. And but in real time, you'll already have data which is already computed with the features. So exactly you can refer to that path and to be able to fetch those data or ingest the data into the feast code. So here we have generate trips. These are the random snippets which we can use for generating random values. So here we are generating this many columns. This is the data which we are going to use for our one of the feature tables, which is basically driver statistics. Okay, so we are going to generate stats. Now we are going to call these functions, and we are going to say that we have three variables which are having the whole data as per our requirement. So now we are going to use a client whichever we have and going to ingest the driver statistics. This is the table, feature table, and the data for that is the stats df which we just created here. So now when we do the ingestion, yeah, so removing the temporary files which are already there, and now we have added successfully ingested into the feature table. So now that we have ingested the table, ingested the data into the into the feature store. Now this is it, you can see that it's just as simple as that. You just have created, you have ingested the data into the feature store. Now anybody who has access to the same servers can easily fetch it from there, fetch it from there, from the feature store, if they know the name or the characteristics of or any information about the feature entity or the feature table. If they know about that, they can easily go and fetch the data whatever they need. So now I can show you how the data is being fetched out from the feature store. So now here we can see there's a read package, a function which actually reads even if it's a file, if it's GCP GCS path, or if it's an S3 path. So this is a small snippet which we have written so that it can be used to fetch the to support all other cloud platforms as well, just for reading. This is something which the engineering team has to do in their own code, so that they can pass based on they can refer any cloud platform. So here is something. Now we have to, in order to fetch the data, now there's a something called as there's an entity which has been created, which has driver ID and some timestamp, and we have two feature tables which has all the computed values. Now we need to fetch, so in order to fetch the values, we have to pass input some driver IDs. Like for these are the drivers for which I want to get the computed values, or if I want to fetch everything also, you can do that. So here I'm using the snippet to generate random driver IDs. So this is the same code which we have used for generating the driver ID. So we won't have values which are not there. So these are the driver IDs which have been generated. So once I have this, this is something I have named it as entities with timestamp. So this is with a timestamp. So here what we have mentioning in terms of timestamp is, so whenever so the data which we already have will have a different timestamp, but the driver ID can have multiple timestamps, because in multiple times multiple same driver could have been updated the database multiple times. So once we do that, the time which is closest to the event time will be returned. So if the single cell driver has multiple rows, the time which is the most recent one will be returned. So that is how the core feast core actually works. So if you want to modify that, we can make some changes, or we can extend the feast library as well. So we have this drivers now. So this is the main part where we are going to get the historical features. Now historical store, as I already mentioned, is a store where we are going to have all the previous versions and everything of the feature of the table of the data which we have ingested. So here but how to fetch is like we are using the same client. We are going to use the get historical features as inbuilt function of it, and we are going to refer what are the features which we need. So here you can see we are referring from two tables, driver statistics as well as driver trips, and we are passing the entity source as entity with timestamp, which is basically this one, this data frame. So when we are passing this one, it is going to join all the three tables based on the primary key, which is driver ID, and it is going to fetch us on these four columns. So if you can see here, I'm just going to create a client and I created a job. Now I'm going to run this job in job as a Spark job, and it is going to run for a few seconds, and then it will join everything, process everything, and it will give us uh, output, which is basically like something like this, which I just ran a few minutes before. So this is the driver ID which you have passed, and this is the event stamp. And now here you can see that the average daily trips, conversion rate, acceptance rate, and the trips today from a different feature table itself. So you'll be able to fetch all the data from the feature store. So the all you need to know is what is the format and how the what is the driver ID, which will be easily accessible from any for any person in the team. And we need to know what are the feature table names and what are the features which are available in the table. So once you know that, you can directly connect to the server and you can directly call this via API, and you'll be able to fetch the features instead of generating these features on your own every time for each and every new data set. So this is one of the biggest use cases of Feast. And so in terms of this, now you can see that this is a retrieval from a historical feature store. Now, as I told you, there's in the architecture, there's a connection between the offline and the online store, which is basically the sync which has been established between offline and online store. So here you can see there's a function in the client which is start offline to online ingestion. So once we have the off, we have once we have trained the model with the set of data, now we want that data to be ingested into the online store to validate the model in production. So you can directly call this API. You can call whatever data you want to send. So driver statistics is a feature table. We're just sending that feature table to online ingestion, which is the online store. And what are the date time we are passing? We are passing from 10th to 20th. So for this 10 days data is going to get ingested into the online store. So once that is done, so we can see this so this is some this response is not, I did not run it now, it ran before. It took around, it will take around 5 to 10 minutes to complete all the three jobs, and it will fetch store everything from offline to ingest everything from the offline store to the online store. Offline is basically historical store. So once that is done, you'll be able to, this is again, I'm generating some random driver IDs to fetch the data. So now I'm going to get the data from the serving layer, which is the online store. From online store, the models can directly fetch the data. So here we are going to get online features, same thing as we saw from the for the historical data. We are going to pass the entity sample, which is the driver IDs, and we are going to refer what are the feature tables and the features we need. So once we mention that, then we'll be able to see these other features which we have got. So yeah, the process is still running, I think. So we are getting null. Okay, so this process is done now. So we are able to see the values here. So I'm going to perform this job again so that it will be pushing it to offline to online. So we can keep checking the status of the Spark job. It will take some time, so we'll be able to see that this is something which we'll be getting out of the features, like once you get it from the online feature. So once this is already processed and the data is available in the online store, you can see how fast the API is. Like you will even though we have tested this with the heavy database as well, but the API it has a very high throughput and very low latency. So yeah, I will be able to fetch the data within milliseconds. And so this, we are just converting the data into a data frame. So we are saying that the data, the IDs which we pass, we are able to fetch those data from the online store. So this is another this is from the online store. So we have seen the historical retrieval from the historical data and the retrieval from the online store. And we have the another example which is from streaming directly from Kafka, which is like a real-time streaming of trips. So here you can see we are trying to connect to Kafka server 9092, which is running in our local as a docker container. So and this is some kind, these are the Kafka basics which we need to know before we can run the real-time run the Kafka streaming job. So this thing we can see here is like the driver type is one of the feature table where we are modifying the stream source. Before it was a file source and we have mentioned the file path for derivatives, but now we are modifying it to a Kafka source. And we are saying what is the topic which it needs to listen, and what is the message format. And this is the schema for that. And once you start stream to online ingestion, it is going to stream to online ingestion. So basically a Kafka broker is going to send a message, like basically is going to publish a message, and once the message is being published, the feast core is going to push that message into an online store directly. So once that is done, so this is a job which keeps running on the background. So whenever a message is pushed into that particular topic, the consumer will pull that message and put it into the online store. So that's what this job actually does. So this is the code for that. And we are having this is what we are producing a message. We are going to read through all our trips tf data frame and going to send each and every record to this topic. So it will get message will get sent, and this job will pick that message and put it to the feast online store. And then we can directly generate some ideas, and you can directly get online features again. And we can, this time we are going to get average daily trips, which is the one which is already present, and the one which we have added now using the Kafka stream is trips today. So these are the real-time data which is being pushed in using Kafka streaming. So when we put that, we'll be able to, initially it will be none because there are no values associated with the driver ID. So once we start pushing the messages using the Kafka stream, we'll be able to see that these values will change to the values which we have been pushed, which we are pushing. So that's how this works. When you want to cancel the job, we can cancel it here because the job will keep running in the background. So this is how the streaming works. You can do the same in any cloud platform using the services provided by the particular platform. So this is how we this is the things which are supported by feast as of now. And how to achieve that, and how to make use of feast as a feature store, and you don't have to worry about consistency in the data and point in time data, because the real time data is also being directly ingested into the store, into the online store. So these are the things which actually feast provides. Do you have anybody has any doubts regarding this, or do you want me to run and show something specifically, or any kind of doubts in this particular part? Okay, then I think yeah. So if you don't have any other doubts, then I think that is pretty much it for today's actually session about Feast, which is a feature store which helps in centralizing the features and helps in improving the feature engineering process. And it can be integrated in any cloud platform, and that's why they call it cloud agnostic. So yeah, that's it from my side for today. If you have any other doubts, you can ping me anytime offline, and we can connect, and we can, if you want to implement this or any other feature store for your project or anything, you can ping me anytime, and we can have a discussion offline to how to understand the requirement and how to implement this in your existing architecture. Okay then, guys, thank you for your time in your busy schedule. Thank you for attending this.
Thank you.
Thank you.
Thank you.
Thanks, Alabama.